Hi, my name is Scott Simpson, and today we'll be talking about the Hamiltonian operator and a little bit about the Schrodinger equation. So, the Hamiltonian operator as you know, it's an operator, so it acts on a function. So you get an eigenfunction, eigenvalue problem in this case. It's given the symbol h hat, and it's used to determine the total energy of a system. So if we have our h hat operator operating on some wave function psi, we should get the energy out and that same wave function back. So now what we're going to do is we're going to look at the time independent Schrodinger equation. So there's the time dependent Schrodinger equation, which depends on time. In this case, we're going to assume time doesn't influence our wave function at all. The other thing is to make it a little bit simpler, we're only going to consider a wave function traveling in the x direction. We're not going to consider in multiple directions. So therefore, what we're going to look at is that Hamiltonian operator, our wave function that depends on x only as a function. So we got the time independent Schrodinger equation, E psi x. So we're, again, this isn't a multiplication, it's showing that the wave function is a function of x. Okay, and we know about energies, we're trying to get the total energy. Energy can always be thought of as two flavors, potential and kinetic energy. So we know that our total energy, E total, or in this case just E like we have, is a combination of the kinetic energy and the potential energy. So what we can do is we can take our Hamiltonian operator and we can split it apart into kinetic energy and into potential energy. And that's exactly what we're going to do. So we're going to say h hat psi of x is equal to, we're going to split h hat up into kinetic energy operator, capital K hat, and a potential energy operator, B hat. Okay, so now let's try to figure out what these operators look like. So let's first tackle the kinetic energy operator. That one's a little bit easier to understand. We know kinetic energy is the energy of motion. Potential energy is the energy due to position or configuration, depending on what we're talking about. From classical mechanics, in physics, we know if we're looking at the kinetic energy, it's the momentum of that system squared over 2m. From quantum mechanics, we know that everything has to exist as an operator. If we have an operator and some value that we want to get out of it, some observable that we want to see, we have to operate with an operator on that wave function to get it out. We know that the momentum in the x direction operator is given by negative I h bar, which is just Planck's constant divided by 2 pi, but we shorten it to h bar, and a differential with respect to whatever direction we have here. In this case, it's x. Okay, so then if we try to conglomerate these two things together, therefore, we're looking for k hat. Again, that's a capital K, different than the lowercase k, which is used sometimes in solid state physics. We have px hat squared over 2m. Let's plug this in. So we should get negative I h bar e dx, all of that squared over 2m. Okay, so we have negative 1 squared that results in positive 1. We have I squared, which it's the square root of 1, so if we, or negative 1, excuse me. So if we square that, then we're going to result in a -1 value, and then we have this differential which we're going to just square. So what the result ends up being is -h bar squared 2m times the second derivative with respect to x. Okay, so now we have this portion of our wave, or of our Hamiltonian, of our Schrodinger equation. What about that potential? So the potential energy operator is a very specific operator to what system you're looking at. So it changes with every system we consider. Before we do that though, our equation becomes, so we have k hat, b hat all operating on our wave function x, or excuse me, psi of x, and we just said h bar, -h bar squared over 2m d dx squared. B bar, or b hat, gets us to this. And again, we know if we evaluate this, we're going to get the energy out and that same wave function. Okay, so what about our b hat? Well, like I said previously, it depends on the specific system. So if we don't know, we have to know a little bit about the system before we can say anything about that potential energy. So it is system dependent. To make our lives easy, we're going to say it depends on position. And many times in physical chemistry, we assume that this potential is 0. For the simplest systems, just to show you further on and explain how to utilize the Schrodinger equation. However, when we get to more tough systems such as the harmonic oscillator or particle in a finite well, this is going to change quite a bit. So just keep that in mind. But for now, for simplest cases, we usually approximate this to be 0. Okay, so now, this equation, what it becomes is a little bit different. We lost the hat here. Now we're going to say that the potential is just a function of the position. And we get this. So this is the time-independent Schrodinger equation that we're going to look at. So now let's consider an example. This one's simple, not the simplest particle in the box, but still relatively simple. I think it illustrates a good system to first investigate and to consider and look at your Hamiltonian and say, okay, what do I need in my Hamiltonian to solve this problem? So our example, consider an electron confined to some system with a wave function of square root times cosine k pi x, where this lowercase k is just some constant. Okay, the other thing we're going to say is if the system has a constant potential of V naught. So it's just some constant. We're going to ask, what is the total energy of the system? Of the system. Okay. So now we have to consider what our Hamiltonian is going to look like. Again, we have to start with the most basic equation we can. H times psi is equal to E times psi. First thing we're going to assume is that this system is time independent. So our psi doesn't depend on time. Makes it a bit simpler. What other approximations can we make? Well, we're told our wave function. Our wave function only has one variable in it. It only has x. So that makes it a little bit easier when we consider the kinetic energy operator. So let's plug in what we can. So we know we're going to have negative h bar 2m. Since we only have a function that depends on x, we get the second derivative with respect to x squared. Our potential, we're told that we have a constant potential of V naught. So, we have V naught there, and now we have to have our function here. So our function is square root of 2 times sine k pi x. Okay. Let's break this apart. Basically, we have psi times these portions here. So let's look at our wave function times the kinetic energy operator. Well, we'll look at the kinetic energy operator operating on our wave function first, then we'll look at the potential part. Okay, so we've got negative h bar squared over 2m. Second derivative of x squared sine k pi x. Okay, so in this one we have to use the chain rule. We have negative h bar squared 2m. Let's just take one derivative first. When we do that, whatever's in front's got to come out. We're taking the derivative of sine, so we get negative cosine. So the result we should get is negative k pi times square root 2. Oh, oops. This should have been cosine, I'm sorry. We're taking the derivative of cosine, which results in negative sine, times sine k pi x. I'm sorry about that. Oh, we need one more parenthesis too. Okay, now we take another derivative of this. Taking derivative of this guy, we should pull everything out, should get negative k squared pi squared, because that first part's just going to come out, times 2 derivative of sine is cosine, so we get cosine k pi x. Simplifying this a bit further, we get h bar squared k squared pi squared over 2m square root of 2 times cosine k pi x. Okay, you might be asking me, why am I leaving the square root of 2 out here? Why am I not incorporating that in? Remember, we have to get the original wave function out from our original equation, or else we don't have an eigenvalue, eigenfunction problem. And this operator wouldn't be, this function wouldn't be an eigenfunction of that operator. So we have to make this true to happen. Okay, so we got the kinetic energy part. Let's work on the potential energy part. So in that case, it's just going to be this cosine squared function, or excuse me, this cosine function times V naught. So for our potential energy part, kinetic energy part, let's conglomerate everything. We would get h bar k squared pi squared over 2m times square root of 2 cosine, we got k pi x, right? Okay, plus b naught times square root of 2 cosine k pi x. Okay, if we simplify this, remember we have to end up at some form like this. We got to pull our original wave function out. If we do that, so h bar squared pi squared 2m plus b naught, all of this multiplied by square root of 2 cosine k pi x. Okay, we're almost there. So that's after the Hamiltonian has operated on our wave function. Now we have to say what the energy is. This right here, this term of all of these constants, that is our energy. Energy is equal h bar 2, or h bar squared, k squared pi squared over 2m plus v naught. Okay, so hopefully you have an idea or a greater appreciation of what the Hamiltonian operator is, how to look at a problem and determine what do you need in that Hamiltonian operator to evaluate and to solve for the total energy of the system. All right, so if you have any questions, please leave a comment below or feel free to email me. Thank you for your time.